Hello, everybody, and welcome back to General Science. It's been a while since we've been here, but it was my spring break with my son. I was spending time with him, so science had to be put on hold for just a little bit. Anyways, today we're going to be doing our last physics video of the series, and then we'll be moving on to geology and the earth sciences to finish up our look into science. Please like, subscribe, and ring the bell so that you can know when these videos come out. It'll also help me understand what you enjoy watching, and I can then make more videos that will help you learn what you want to learn. So let's get into today's topic, and that is thermodynamics. It's going to be kind of the last thing we talk about physics-wise. And basically, thermodynamics is the branch of science that deals with heat and its relation to other forms of energy, right? So we've talked about energy before. We were talking about like mechanical and kinetic energy, but now we're going to be really talking about like heat and the other types of energy associated with that. So what exactly is thermodynamics? Well, it was developed out of a desire to increase the efficiency of steam engines. So back in the Industrial Revolution, steam engines were invented, but they weren't super efficient, right? They were kind of new, and so there was this desire to make them more efficient and so they can do more work for us. And so thermodynamics kind of developed out of that desire to kind of increase productivity. Now, after a while, we ended up realizing that this doesn't just apply to steam engines, and we ended up also realizing that it applied to the energy within chemicals as well. And so we kind of branched out and learned more about the thermodynamics of chemical equations, chemical reactions, stuff like that. So the first thing you need to know about thermodynamics is that everything we do in thermodynamics is studied through the work of what's called a system. A system is just a precise region of the universe that we're studying at that exact moment. And that's really important because if we generalize too much, we're going to have too many factors to deal with, right? So we have to precisely pick exactly what it is we're looking at. All things outside of the system we pick are called the surroundings. So an example could be this room, right? I'm sitting in this big room. Okay, that could be my system, even that's pretty big. And then everything outside of these four walls, right, is then considered the surroundings. And so if I was going to do a thermodynamic study of this room, right, we'd be processing the heat and energy transfer in here, right? I'm generating heat and pushing it into the system. And then potentially, right, if I have my window open, right, heat might be escaping out into the the world. That'd be leaving into the surroundings. So that would be kind of why we have to define these things so we know where our energy is going. Now, the other thing that's really important when it comes to thermodynamics are the laws of thermodynamics, and there are 4 laws, and they're kind of oddly named, and we'll explain kind of why they are later. But we'll start with the first one, which is actually called the Zeroth Law. Now, the Zeroth Law of thermodynamics, you didn't know zero could do that, could you? It basically says that if 2 systems are in thermal equilibrium with a third system, then they are also in thermal equilibrium. Now, what does equilibrium mean? I just put a new word out there, right? Equilibrium is when the flow of heat energy has stopped and the 2 systems' temperatures aren't changing anymore, right? So you could imagine, right, if you had 2 different boxes and they were sitting next to each other and they started off at different temperatures, right, their temperatures might change until they were both the same temperature. That's equilibrium. So why is it the Zeroth Law? Well, they added it later because it's actually implied in the other laws of thermodynamics, but they never really specifically wrote it down. And so then finally they were kind of like, we probably should. And so instead of rewriting all the names of the laws, right, renumbering them, they just said, okay, we'll stick it in front of it and call it the Zeroth Law because this one's actually really important. So that's the Zeroth Law. The first law, which is actually the second one, right, says in a process without transfer of matter, the change in internal energy of a thermodynamic system is equal to the energy gained as heat, less than the thermodynamic work done by the system on its surroundings. And that basically just says that energy is conserved. So it's a really complicated way of saying that, but basically it means that energy can't be created or destroyed, and that it can be transformed or transferred to different things, but we can't just lose it. It doesn't just disappear, right? We can always track down where this energy went if we lose it. And so that's what the first law says, right? That energy can't be created or destroyed is basically like the layman's way of saying it. Now, the second law says that heat does not spontaneously flow from a colder body to a hotter body. which means, right, that let's say we had something that's been constrained, right? We have these really, really solid walls around something, maybe a heat source or something, right? And we slowly take the constraints away. That heat is going to try to escape randomly and chaotically. And what that really means is that there's this thing called entropy. Entropy is the idea that there's disorder and chaos and uncertainty in the universe, right? I know when I first learned about entropy, they always said, like, if you imagine your bedroom, right, and you clean it, you've ordered it, right, in this exact way that you've wanted, it's really clean, your parents are happy, they're like, yes, Mike finally cleaned his room. That was a big thing in my house. If I cleaned my room, it was a big deal, right? Well, over time, that order is going to slowly decay away and chaos will spread and my room will once again become messy, right? It happens even now. I'm an adult. My spaces in my house get messy. And that's what entropy is, right? There's always this constant of disorder and uncertainty in the universe. And that's what the second law is really defining. It's saying that this disorder exists and we have to factor that into our calculations. And then finally, the third law says that the temperature of a system approaches absolute zero, right? Really, really cold. All processes cease and the entropy of the system reaches a minimum value. Now, what does that mean? Absolute zero is the temperature where atoms stop vibrating, okay? So even solid things, like I've got this shelf next to me, right? It's solids made out of metal. Okay, the atoms in that shelf do vibrate. It's not very big, right, the vibration, or it doesn't have a very big magnitude, but they are vibrating, okay? At absolute zero, atoms stop vibrating. There's no more motion, okay? That's we thought it was 0 Kelvin, but we've learned that we can actually go beyond what we thought 0 Kelvin is. So we're still trying to figure out what exactly that temperature is. What is absolute zero when we can stop atoms from moving? It's something scientists have been working on actually a lot. Okay. Now, why does entropy reach a minimum at this point? Well, it's because, right, since the atoms are no longer moving or they're going so slow that they're not moving very fast, there's no more disorder, right? They're all rigidly locked into place. They're not moving, and so it's eliminated, or at least minimized, that disorder that happens in the universe because atoms move and shake and bounce and jump all over the place, right? So since they're no longer moving, that disorder has been eliminated or minimized. Now, the last thing we need to talk about, okay, when it comes to thermodynamics, before we hang up our lab coats for the day, okay, is the Gibbs free energy. Now, this value, which is represented by a G, okay, is the amount of energy available for something to do work with, right? So, for instance, a car engine could have, or like the gasoline for your car has amount of Gibbs free energy. It's the amount of energy that gasoline can use to do work to make your car go. Or your body might have an amount of Gibbs free energy, the amount of energy available for your body to do work, to move, to exercise, to do whatever, right? That's your Gibbs free energy. Now, this is also used to apply to things like chemical reactions, right? So it's the amount of energy left available after your chemical reaction has reached equilibrium. And these things, this value is very important because it kind of shows how much energy is actually available to do things with, right? If you have a big store of energy, but you only can use this much of it, right? That's kind of important to know, especially when you're dealing with like the efficiency of an engine or something like that. So to calculate it, you have to make sure that you have constant temperature and pressure, and then you also have a closed system, which is kind of important. It's something that scientists work an awful lot about when they're doing thermodynamics, is making sure that their system is closed, which means that energy can't escape it. There is an equation that goes with Gibbs free energy, and that is big G, which is Gibbs free energy, is equal to H, which is the heat, right, minus the temperature of your system times the amount of entropy. Entropy can be calculated. It's an actual number that you can quantify. So you multiply those two things together and subtract it from the heat, and that gives you your Gibbs free energy. Whew, so much thermodynamics. Next up, like I said at the beginning of the video, we are going to be moving on to geology, environmental science, earth sciences, and all that fun stuff. It's a big kind of wide-ranging area, so we're going to cover lots of different things, talk about lots of different cool stuff. And that's where we're going to end our series. After we finish talking about all that, we're going to be pretty much done with general science. Now, don't despair. We may be coming back to do more physics later. I've got to try to get someone to come talk with us, have a guest on general science who can talk a little bit about modern physics, the kind of things that I don't really understand and can't really help you guys with. So if I can get that lined up, we'll come back later and we'll talk about that at a later date. But until then, our next video will be moving into those geology, environmental science, and earth science kind of scientific inquiries. Thank you once again for watching. I hope you subscribe, and I hope you enjoyed watching general science. We'll see you next time for some geology. Let's go rocks.